in this video, we will start our lesson on transcendental curve sketching. So, this is technically still part of calculus. So, let's say we have this curve, function. So, consider this. Y is equal to f of x such that y is equal to x minus 2 over x squared minus 7 is equal to 2. Okay, let's just focus on this. So in transcendental curve sketching, we look for 6 things. So let me just number them down. We have to look for the domain, the intercepts, asymptotes, basically the VA and HA, horizontal and vertical. Symmetry, determine whether the function is symmetrical with respect to the y-axis and or the origin. Also critical points you have to identify. I should have made a video already before this on critical points, maxima, minima, as well as point of inflection. But I don't know, it's not easy to teach that lesson. But in regards to the concept of critical points under the context of curve sketching, I can teach. So yeah, number 6 is region analysis. Then we graph. So similar to piecewise functions, we look for some values that we need so that we can make a graph at the end. So let's go back to our example. Let's try finding the domain. So how do we do that? Again, what is the definition of the domain? So these are any values of x that make the function undefined. So essentially, for polynomial functions, there are no values that make it undefined. But it's a different story for rational functions, such as what we have right now. So as long as we see a fraction, basically a numerator and a denominator, then there is a good chance that we would have a value that is not part of that's basically going to make the function undefined. So it's not considered an element. So in this case, what will make this function undefined? So if you think about it, let's try x equal to the square root of 7. So in that case, x squared is square root of 7 squared. That is also equal to 7. So in that case, the denominator will be equal to 0. And at the top, square root of 7 minus 2. You don't have to know whatever that value is exactly, but essentially, this value is considered undefined. Therefore, for our domain, it's gonna be x is an element of all real numbers except such that x cannot be equal to the square root of 7. Also, ideally it's the same thing. Square root of negative 7 cannot also be part. So this is one way to write the domain. Another way, the longer version, is this. So x negative infinity less than x less than negative square root of 7 union set union negative square root of 7 square root of 7 union square root of 7 less than x less than positive infinity. So really it's a longer render of the domain, but I believe this will suffice. So that's it for the domain. In transcendental curve sketching, you have to memorize, obviously, the 6 things that you have to find. So what's an acronym for it? We have domain, intercept, asymptotes, symmetry, critical points, it's abbreviated as P. And then, actually, for critical points, it helps if you abbreviate it as PO. And then for region analysis, RA. So we have the abbreviation diaspora. So that's one way that can help you remember. You can make your own abbreviation, whatever helps you. So let's move on now to intercepts, I. So when it comes to intercepts, we have the y-intercept and the x-intercept. So how do you find the x-intercept? Sorry, this one first. How do you find the y-intercept? So this is assuming that your x is going to equal to 0. So copy this function. I believe you just substitute. Let me confirm if that's correct. Yes, you do. So 0 minus 2, 0 squared minus 7. This is going to be 2 over 7. So 0, 2 over 7. This is our y-intercept. For our x-intercept, we'll assume that y is equal to 0. So using the same function, we substitute y as 0. Then we solve for x. So when we multiply both sides by x squared minus 7, we have this, then x is equal to 2. So we have the coordinate 2, 0 for our x-intercept. We are done with intercepts. Let us now find asymptotes. So we have the vertical and the horizontal asymptote, right? How do we find the vertical asymptote? So let's copy the function again. This is somewhat still a gray area to me, so I might not be able to explain the essentials, or I might not be able to explain it properly. So I just want to inform that to you immediately. So as far as I understand, it involves something with the limit. So limit as x approaches a of x minus 2 over x squared minus 7. Earlier, we have to consider that what makes the function undefined is if x is equal to the square root of 7 or square root of negative 7, right? So we will use those values. A, that's going to be basically our A, right? So in that case, y is equal to square root of 7 minus 2 over 7 minus 7. That's going to be equal to c over 0, right? And according to, I can't really specify what that is, but I was able to teach that a few videos back, somewhere in theorem of infinite limits. Essentially, this one is equal to positive infinity. Let's try this. So negative c, never mind about this. Let's go to horizontal asymptote first. So we want to ask this question: is the limit of f of x as x approaches infinity equal to the horizontal asymptote. So again, we have this function, right? So the limit as x approaches infinity, we directly substitute infinity minus 2 over infinity squared minus 7, infinity over infinity. We have an indeterminate form. So because we have an indeterminate form, we can say that the function has a horizontal asymptote. As far as I remember, if you directly substitute and your answer is not considered an indeterminate form, it indicates that you don't have a horizontal asymptote. So try to remember that for the next example later. If I remember correctly, that example exhibited what I just said. So yeah. So what do? We apply L'Hopital's, right, to find the limit. So 1 over 2x. Then let's try to directly substitute again. 2 times infinity, we have a constant over infinity. This is going to equal to 0. Therefore, this is our horizontal asymptote. Also, one thing that you'd want to know, if the limit does not exist, the horizontal asymptote would also not exist. Again, finding vertical asymptote is still quite of a gray area to me. Let's move on to symmetry. So let me just show you something. So for symmetry, these are the guide questions. You'd want to ask, is f of x symmetric with respect to the y-axis? So in order to identify if f of x is symmetric with respect to the y-axis, this has to be fulfilled. So f of negative x has to be equal to f of x. In a similar vein, if f of x is symmetric with respect to the origin, then f of negative x has to be equal to negative f of x. So that's the theory. So in our example, let's copy the function again. Let's assume that we'll have negative x instead. So negative x, negative 2, negative x raised to 2 minus 7, negative x, negative 2, x minus 7. So f of negative x is not equal to f of x. Therefore, we can say that there is no symmetry with respect to the y-axis. What about with respect to the origin? Again, the policy is for symmetry with respect to the origin, f of negative x has to be equal to negative f of x. So let's see. I think it is fulfilled. Let's see later. We will be able to confirm uh, with more confidence once we see what the graph looks like. For now, critical points, PO. So basically for this part, you get the first derivative, or you can get the second derivative in order to determine maxima, minima, and possibly the point of inflection. Although so far, at least from my experience, I didn't encounter any point of inflection. After finding the derivative, we equate to 0. And the rest is history. I am basing on the lecture of my professor, and apparently there's no solution in this part. Let me synthesize something. So after equating to 0, we identify the x values. Okay, this looks weird. We have two more examples anyways. We can skip this part. Let me just show you what happens after finding critical points. So, region analysis. These are the guide questions. So we create a table of values using the roots. The roots, by the way, are 2, square root of 7, and negative square root of 7. Where did we get 2? Let's see. Most likely it came from the x-intercept. I am certain there is a connection. We'll go through regional analysis later. I can assure you the other two practice questions will have they have complete solutions. So let's try y is equal to x squared e raised to negative x squared. So again, let's find the domain. What will make the function undefined? Since this is a polynomial function, it's not a rational. So we can say that x is an element of all real numbers. In other words, no values of x will make y undefined. How about intercepts? So let's say x is equal to 0. Let's solve for y. Y is equal to 0 squared e raised to negative 0 raised to 2. Essentially, it's 0. So this is the y-intercept. What if y is 0? How do we rewrite this? reciprocation, I guess. There you go. And we solve for x. So it just so happens that both our x and y intercepts are the same. So they are on the point of origin exactly. Now, asymptote. So since the domain of f of x is the set of all real numbers, let me write that down. Since domain is all real numbers, we don't have a vertical asymptote. So that's the condition for the absence of a vertical asymptote. To find the horizontal asymptote, so limit as x approaches infinity always, and then we just copy the function. So essentially, the horizontal asymptote is the limit of the function as x approaches infinity. That's why we write this down. So let's try to direct substitute. Infinity divided by e raised to infinity is still infinity. So we have an indeterminate form. Then we apply L'Hopital's rule. So we can find the limit. 2x over how do we derive this? D over dx of e raised to x. E raised to x du over dx. What if it is ex squared? Okay, I think that's it. So that's the derivative of for the numerator and the denominator. Then we cancel. What we have left is e raised to x squared. If we substitute, then we have 1 over infinity. A constant over infinity is equal to 0. So this is our horizontal asymptote. Now, let's go to symmetry. So, f of negative x negative x squared e x e Let's rewrite. Okay, so clearly it is still equal to f of x. So we just confirm that our function is symmetric with respect to what? With respect to the y-axis. That is it. I think you don't have to look for symmetry with respect to the origin anymore. It's either with respect to y-axis or the origin. Although that's just my hypothesis. Critical points. Again, this is our function, right? So we find the derivative. Quotient rule. By the way, when you try to simplify this, it's not equal to e raised to x raised to 4, okay? This one is not an exponent to this. This one is a base to this. So essentially, it's going to be e raised to 2x squared. The 2 here is multiplied to x squared. It's not raised. It's not x squared raised to 2. So that's why we have this. Then we equate to 0. We try to find x. I think we can factor something. Then no. Bad idea. So what x value will make it the entire thing equal to 0? Anything that's multiplied to 0 is 0. So let's try x equal to 0. So it's most likely 0, for sure. Therefore, x equal to 0 is one of the values that we want to find. And here, we have positive 1 and negative 1. So, what do we do with these values? That's where we base our derivative test on. Either we use first or second derivative test, whatever is more convenient. It just so happens that in this practice question, first derivative test is better to use. So yeah, also before we do that, we can identify the y value that corresponds to these critical points. So for f of 0, we go back to the original function. So f of 0 is equal to 0 squared over e raised to 0 raised to 2. 0 raised to something is going to equal to 1. But 0 over e raised to 1 is still 0. So we have 0, 0, I believe. Mm-hmm. What about f of 1? So we have 1 over e. That's it. How about f of negative 1? So negative 1 squared over e raised to x squared. 1 over, same thing. Okay, so we have the coordinates already. We want to determine the behavior of these points. If they are local maximum, local minimum, or possibly point of inflection, or possibly global maximum, global minimum. So let's apply derivative test for x equal to 0. By the way, for first derivative test, what we do is find a value from the left and from the right. But make sure that that value is not equal to any of the other critical points. So yes, technically from the right, a value from the right of 0 could be positive 1, but we don't use 1. We can use 1/2, if you get what I mean. So from the left, we can't use negative 1. We can use rather negative 1/2. So like that. And also x is equal to 1/2 from the right. So what do we do then? We copy the first derivative of the function. Then we substitute the values. Then we simplify. So 2 times negative 1/2 e raised to negative 1/2 squared minus 2 times negative 1/2 cubed e raised to negative 1/2 squared over e raised to 2 times negative 1/2 squared. Further simplify. Where did I get 8? That's supposed to be 4. Here. 2 times 1 over 8, that's 1 over 4. Okay, makes more sense. So over 4, and this is supposed to be positive. Negative 3 over 4, e raised to 1 over 4 over e raised to 1/2. Essentially, what you have to know from this value is whether it's negative or positive. In this case, because of the negative sign, it is a negative value. Therefore, x equal to 0 or its coordinate 0, 0 is a local maximum. How do you know that it's a local maximum? That's because we have a negative value. If it's negative, then wait. My bad. I was thinking about second derivative test. That's the reason why we have x is equal to 1/2. We need to substitute all the way from the start. So we don't have the final say yet unless we finish, we identify whether after substituting the value would be positive or negative. That's when we determine if a critical point is a local max or minimum. So essentially, it's a positive value. So coming from a negative to a positive value, that means 0, 0 is a local minimum. So take note of that. From negative to positive, that means local minimum. And if ever you're wondering, what if it's the other way around, from positive to negative? Then logically that is local maximum. Now you know. So that's just for one critical point. We have 2 more to go. For x is equal to 1, we can say from the left, it's 1/2. Same thing. What we found for 1/2 turns out to be positive, so we don't have to repeat the same process. What's at the right of x equal to 1? 2. 2 is not considered a critical point, so we can use it. So again, the first derivative, substitute, okay, so looks like this is a, yeah, it is a negative value. So coming from positive to negative, 1 over e is a local maximum. Okay, for x is equal to -1, let's say from the left, negative there's a reason why my solution paper no longer showed the one for x is equal to -1. Maybe it's probably because, if I remember correctly, it had to do something with the symmetry, symmetric with respect to y-axis. That's why we only either needed to find the behavior of x equal to 1 rather than x equal to -1. Although either way, if you found this instead of this, it doesn't change anything. Maybe it has something to do with this. Their y values are the same. So symmetrical with respect to the y-axis. So after critical points, we now identify region analysis. So RA, right? So what are the roots? Let's make a table. So where is our function again? Let's rewrite this as a fraction. Avoid any negative signs in the exponent value. So essentially, for the numerator, we have x squared. The denominator is e raised to x raised to 2. And the entire thing is this. This is how you make the table, okay? Then you identify the roots. What are the roots? So coming from the intercepts, clearly, we only have 0. Also, considering the horizontal asymptote, we only have 0. So that's the only root, actually, for this problem. Therefore, put 0 over here, and vertical line below it directly. Then, shade these parts. We don't need it. If we only have one root, then we only need this part. So, what you want to do now is substitute any value in this position has to be greater than 0, obviously, and any value below it has to be less than 0 at the left. So let's say 5. Let's substitute 5 in x squared. So 5 raised to 2 is 25. 25 is a positive value, so positive. And then say -5, still positive. E raised to 25, still positive. This is still also positive. 25 over, this is still positive. Still positive. At this point, to find these, I think it has to do with multiplying or dividing. It makes more sense if you divide. So positive divided by positive is a positive. Same thing here. So let's start graphing now. So this is our Cartesian plane. What are the intercepts? So both are 0, 0. What are our critical points? So one of them is still 0, 0. The other two are those. So in the x position, we have 1 and -1. 1 over e, let's say this is 1. 1 over e is somewhere here, right? So these are the two critical points. What else? If you ask what's the relevance of this table, unfortunately I don't remember anymore. It's been a while since I studied this. 2 weeks ago, since I took the final exam. For the horizontal asymptote, it's 0, right? So basically our graph will never touch y equal to 0, but will always go closer to it. That's the meaning of an asymptote for the most part. For vertical asymptote, we don't have, and it says our graph is symmetrical with respect to the y-axis, right? So how do we apply that information here? HA, y is equal to 0. So our graph looks roughly like this. Okay? So that is the graph of this function. That's it. Here's another example, although I won't teach it anymore. I'll just show you my solution. So given that y is x ln x squared, domain, intercepts, asymptotes. You find the roots, by the way, in the intercepts part. Okay. Also, something that you'd want to know is how do you determine if there is no y-intercept? So if, for example, here, there is a value that will make y undefined, that is 0. That's why we exempt it. So in that case, for intercepts, to identify the y-intercept, you have to substitute x as 0, right? But it says here in the domain that 0 cannot be part. Therefore, you don't have a y-intercept. That is the logic behind that. Okay? So, for asymptotes, again, for vertical asymptote, this is pretty vague to me. But for horizontal, again, limit as x approaches infinity. In this example, there is no horizontal asymptote because we did not have an indeterminate form upon substituting. So as you can see, we got infinity. Infinity itself is not considered an indeterminate form. So no HA. And then you have symmetry. So we identified that y is not symmetrical with respect to the y-axis, but it is symmetrical with respect to the origin. And these are the critical points. First derivative, second derivative, equate the second derivative to 0. In this example, it just so happened that the second derivative test was more appropriate to use. So I have shown you how to do first derivative test, but for second, you only need to substitute that value directly. So in this, for example, this is our second derivative, right? 2 over x. So you substitute directly your x value. And if it's positive, then it is considered a local minimum. If it's negative, then the critical point x equal to negative 1 over e is a local maximum. Okay? And then regional analysis, your roots are 0, negative 1, and 1. It came from the intercepts. Okay? So this is a relatively challenging part. But I believe it dictates how your graph is supposed to look like. So in this case, going up and then at the left going down. Essentially, what you put in the graph are your roots, your critical points, as well as your asymptotes. So yeah, that's it for this example. I'll end the video here.